When evaluating or working with logarithmic functions, it's important to look back to what the definition of a logarithmic function is and to really get a handle on the meaning of what they're asking us to find. So I'd like to start this segment by going over the definition of a logarithmic function. So if b is greater than 0 and b is not equal to 1, the logarithmic function with base b is defined by y equals log base b of x if and only if b to the y is equal to x. And a lot of times we get the logarithmic functions form this way through finding the inverse function of an exponential function. Switching the x and y's and then solving that for y, getting the logarithmic form of the logarithmic function, y equal log base b of x. So notice the placement of these. The y is the exponent that was on the base of b to create the value of x. So when I write it back as the logarithmic form, we want to think to ourselves when we read log base b of x as what exponent would I need to put on the base b to get the value of x, and think through it that way. Now, the domain of your logarithmic function is greater than 0 all the way off to infinity, and the range is all reals, or from negative infinity to positive infinity. We have two different forms for our logarithmic functions. If we write it as x is equal to b to the y, the same equation I had over here, only switching the b to the y and the x on the two different sides of the equation. So x equals b to the y, or the logarithmic form, which is y is equal to log base b of x. So if I bring the exponent and get what its quantity is, it's equal to the exponent that I put on b to create the value x. Okay, so here's a few questions that we can apply the information from the definition to answer. So the first one just says, write this equation, 5 to the third is equal to 125, a true statement, in logarithmic form. Well, right now it is in exponential form. Notice I have a base to a power is equal to a value. So when I write this in logarithmic form, I want to notice what each component represents. So in the on the side where I have a base to a power, my base is the b. My power on the base is your y, and then the value that it equals is your x. So when I come over here, I see that I have 3 is equal to log base 5 of 125. So reading this back, the exponent that I need to put on 5 to create the value 125 is an exponent of 3. And that's how that statement has its equation, its equality between the two sides. How about the next one? Write log base 3 of 81 is equal to 4 in exponential form. So this one I have in logarithmic form, it's already in this form, and I want to write it back into exponential form. And practicing this with true statements helps you get a little bit better at it. So then when you have to rewrite expressions that have variables in it, you will see where you need to put everything and be more comfortable with the process. So remember, logarithms are exponents that you put on the base to create that value. So the exponent I put on 3 to create 81 is 4. So I'm going to write 3 to the 4th is equal to 81, my true statement. Now, let's look at 3 different problems here where we want to find the value if they don't give me the other side. And if they're asking me these questions where the quantity that the logarithm is acting on is a perfect power of the base, we're able to do that without actually having to use our calculator. So the first one says log base 7 of 49. So you want to think, what exponent would you need to put on 7 to get the value of 49? Well, 7 to the second power is 49, so I'm putting an exponent of 2 on 7 to create the value of 49. So my log base 7 of 49 is 2. And we can actually even write a because statement about this. It's because 7 to the second power is 49. The exponential form is a true statement. Let's do the next one. Log base 2 of 8. Well, what exponent do you need to put on 2 to create the value 8? We need an exponent of 3 on my base of 2 to create the value of 8. So log base 2 of 8 is 3. And again, we can write the equivalent exponential form because 2, my base of 2, to the third power will give me that value of 8. And then the final one for this segment is log of 10,000. Now, if it's spelled L-O-G for log and there's no subscripted base showing, your assumed subscripted base is base 10. And those are called common logs. So that's equivalent to asking the question, what exponent do I need to put on 10 to create the value 10,000? Well, 10 to what power will give me 10,000? It'll be 10 to the fourth power to give me 10,000. So log base 10 of 10,000 is 4. Well, I hope this introduction to logarithms has helped a little bit. I'm going to make another segment where we do more of the types of problems with finding the log base of quantities that are powers of the base and get you a little bit better at that. And then we'll look at some graphing of logarithmic functions.